Hello everyone, WABYA here, June the 18th, happy Father's Day, and I thought I would make a short video describing, illustrating how to measure receiver sensitivity. Today I'm going to use a common transceiver made by Kenwood. This is a TS2000. It's fairly old. I've had it for close to 20 years. It's still being manufactured, and I'm sure it's had a lot of improvements made to it. So we'll see how its sensitivity rates. We could use any receiver. Could measure the sensitivity of a scanner that I like using to monitor the Air Force jets that fly overhead all the time here from near Fort Wayne. We have the Air National Guard, so we are treated to A-10s and F-16s that fly overhead. It's always a treat for me. I love seeing them flying over. I like listening to them. We could just as easily measure the sensitivity of something like a software-defined radio, which I've done for my own curiosity. But today I'm going to show you how to measure the sensitivity of the Kenwood TS2000. I'm going to use the 2-meter band. I'm going to use a frequency of 144.2. I'm going to standardize my bandwidth to 500 Hertz, which is commonly done when measuring sensitivity. And I've made sure that the IF bandpass of the receiver is flat. In other words, there's no enhancements to the RF or to the AF sections. Pretty much everything is flat. Now, when you talk about the sensitivity of a receiver, we typically use the term MDS to characterize that sensitivity. Now, it's interesting that MDS actually has been around for many years, and it's used by a lot of different people in different ways. MDS can actually stand for Minimum Discernible Signal. It can also stand for Minimum Detectable Signal, depending on who you are and what standard you're using to define that sensitivity. So be aware that there are some differences. What I've done is I'm going to point you to a site on the web. And this is a really good introduction, and it'll explain in a very, very nice way the difference between the two, the minimum discernible signal and the minimum detectable signal. So I encourage you to make a note of that URL and have a look at it. So just as a side note, in my previous life as a Tempest engineer, we would have to characterize the detection system we used to perform our tests, and we used MDS. And it was always referred to as minimum discernible signal. And the standards that we used very, very carefully explained the procedure that we had to use to measure that MDS. I bring that up because, for example, if you go to the ARRL site, there's a very good PDF available, and it explains their test methodology for evaluating radios, and one of the aspects is the receiver sensitivity, and they do define how they measure the MDS. They refer to it as the minimum discernible signal, and I'll be calling it the minimum discernible signal. But just be aware that different people have different meanings for MDS, and MDS can be measured in different ways depending on whose standard you use. So rather than getting into a pissing match with different people about what method should have been used and what standard should have been used, things like that, I'm going to try to make things easy, and I'm just going to duplicate the method that's used by the ARRL as far as their definition for MDS. I'm going to use slightly different equipment than what they use, and that's the reason for this video. I wanted to show you a very easy way to measure the sensitivity without going to the trouble of using the equipment that they specify in their PDF document. The way they do it is 100% accurate, it's acceptable, but a lot of people don't have the equipment that they specify, and this video is to show you that it can be done with a lot simpler equipment. So let's get started. The first thing you're going to need is a receiver, and what we're going to do is in the back of the receiver I've connected the speaker output from the radio, and that's that black wire, and it's coming over here, and it gets connected to an old friend of ours, an HP 3400 RMS meter. The key requirement for measuring the MDS receiver sensitivity is to have a true RMS reading voltmeter. The HP 3400A is just such a beast. Be careful, because there's a lot of meters out there that claim to measure RMS voltages, but they also don't tell you in the fine print that the waveform has to be a very clean looking sine wave and things like that. True RMS voltmeters will measure, give you the true RMS value regardless of what the waveform looks like, and that's what we need here. So I'm going to use this HP 3400A. You can pick them up on eBay. I got this one for probably $40, and the reason it's so nice to use for this is that bottom scale. You'll note that the bottom scale is calibrated in decibels, and that's going to make our life really, really easy. We're going to be using that bottom scale. We're not interested in one bit on what the absolute level is, in other words the voltage of the signal is. We're going to be looking at the differences in dB of the signal, the audio signal coming from the receiver, and I'll get into that more later on. And then I'm also going to show you how we can use a meter like this. This happens to be a Fluke 8920A, and as you can see, it is a true RMS reading voltmeter. And what's beautiful about this instrument is not only will it measure, give you an absolute reading in dBm, and I can dial in any impedance value that I want, or I can press in that button and it'll read dB in a relative scale. So right now, with no input, I've zeroed it and it's reading 0 dB, and this is going to make our life really, really easy. So I'm going to show you how to do it using that meter right there and an old 30 to 40 year old HP analog meter. So that's going to be the 2 meters we're going to use. The last piece of the puzzle is going to be a signal generator, RF signal generator. And in this case, I'm going to be using a Marconi RF signal generator. In this case, it's the 2051. I'm going to use it because it's currently in calibration, and it's a good SIGGEN. And I've got it set up for the same frequency as the TS2000, right at 14.2. We have all the modulation disabled. In other words, we're going to be working with just an RF carrier at a single frequency. So the first thing that you want to do, realize that the amplitude accuracy of your SIGGEN is what's going to be very important here. You want to be sure that when your SIGGEN is set to minus 100 dBm, that it is actually a minus 100 dBm. Or if you put it to minus 130 dBm, that it's actually 130. Those numbers are going to be used to determine the actual MDS, or the sensitivity of the receiver. So you have to have an accurate signal generator where you know the amplitude. Every signal generator, regardless of their cost or make, whether it's a nice Marconi like that, or even something like an 8662, which is a really nice Old Faithful, something nice like an 8657B signal generator. What happens is when you start dialing in lower and lower amplitude values for the RF signal, the tolerance of that amplitude starts getting to be a little bit sloppy. In other words, if I dial in an amplitude of minus 130 dBm, I don't have the spec right in front of me, so don't quote me on this, but I'm just going to make this number up. But if I dial in a number of like minus 130 dBm, the amplitude accuracy may be off plus or minus a dB or dB and a half. If I change the amplitude to something like minus 50 or 60 dBm, the accuracy improves, and the amplitude accuracy may be within plus or minus, say, half a dB or 3/4 of a dB. So for most measurements, it probably doesn't make much of a difference. I mean, if you're off a dB or so in these measurements, it's not going to make a huge difference. But if you're after as much accuracy as possible, what I like to do is set the generator for a level like minus 70 or 80 dBm, and what I do is I bring out the RF signal. Always use a good quality double shielded cable, something like RG142 or RG223, and what I've got it going into is a step attenuator where I can vary the attenuation in 1 dB steps, and then I can also vary it in 10 dB steps. And the output of that we've got going up into a SpecGAN where I am verifying the amplitude and the accuracy of not only the RF signal generator but of the step attenuator that we're going to be using. So let me do a quick example. I'll show you what I mean by that. Right now I've got the amplitude of the Marconi set for 0 dBm, 144.2, The spectrum analyzer seems to be in pretty close agreement. 144.2 is showing minus roughly 0.35 dBm, and that's pretty understandable given the fact that I'm going through an adapter, a connector. I'm going through about 5 feet of cable. We've got more RF connectors that the signal has to pass through here. Got to go through another adapter up there. So given the fact we're going through several adapters and 6 connectors or so, especially up in the VHF frequencies, a slight difference of 1/3 of a dB is pretty understandable. So if I go ahead and punch in a level of, say, minus 20 dBm, you want to make sure I'm just using the SigGen amplitude. You can see that in fact the amplitude dropped exactly 20 dB. I could make it, say, minus 50 dBm, and you can see it's holding pretty steady. So I trust the SigGen and its attenuator that every time I change its level, it's actually going to be true. You also want to do the same thing and verify the step attenuator that you're using. Now I've already verified that in fact every time I advance the 1 dB attenuator I do see a 1 dB change, and when I change the 10 dB attenuator I see a 10 dB change. And I'm not going to go to the trouble here, I don't want to waste your time, but you can see that if I advance the 10 dB attenuator, we do in fact see about a 10 dB change. I can advance it another 10 dB. Let's see if this thing will focus for us. Yeah, it doesn't look like it's going to do too good of a job for me, so my apologies. But you can see in fact that every time I advance dB on the attenuator, we're within 1/10 of a dB or so, and that's more than accurate. If you're within a 1/10 or 2/10 of a dB, you're doing really good. So okay, so we're pretty happy with the results that we're seeing. We know that our SigGen is putting out a true signal. It is accurate. It's been calibrated. We verified it again with a calibrated spectrum analyzer. That's important because we need an absolute level that we can trust. We know how much loss we've got in our cables, things like that, and we verified our step attenuator. So what I'm going to do now is disconnect the RF signal, and rather than going to the spectrum analyzer, I'm going to connect up a cable, a double shielded, probably RG223 cable, and we're going to run it over to the TS2000, right to the antenna port connector. In this case it's going to be a PL259 connector. And let me go ahead and set that up, and we'll show you just how easy it is to measure the MDS. Okay, a couple of real quick points that I want to make here. I'm going to inject this little segment between a couple of the video clips. I forgot to mention that when making these MDS measurements, the RF signal generator is set to generate just a single carrier, no modulation on the generator whatsoever. The receiver in this case is in the CW mode. It was in the CW mode. Could also be in the upper sideband or the lower sideband mode. Any one of them would work. The idea is to be able to detect that carrier from the generator, off-tune slightly so that we can actually hear that carrier within the passband. So you can use upper sideband, lower sideband. In this case I use CW. It doesn't matter. The important thing is that you've got the bandwidth set to 500 Hertz if you want a MDS value that's being standardized with things like the ARRL standard. So that's the first thing I want to mention. Next very important detail is one of the reasons why we like using a meter like this is that it's a true RMS reading meter, and it's got a bandwidth that's quite wide. If I'm not mistaken, this meter has a bandwidth of about 10 megahertz, and it'll still be accurate. That's pretty broad. The Fluke meter is even wider. If I'm not mistaken, I think it has a 20 megahertz bandwidth, where it'll still be a true RMS reading meter. Both of these are more than adequate for measuring the MDS of a typical ham receiver, because we got very, very narrow bandwidths. If we use 500 Hertz or 3 kilohertz, let's say we even went to 5 kilohertz, that's more than narrow enough to easily fit within the capabilities of a meter like this or the Fluke that have 10 megahertz and 20 megahertz bandwidths. But just know that there are times when you're using specialized receivers where the bandwidths are very, very wide. It's not uncommon to use for other types of tests very wide bandwidths, 100 kilohertz, 500 kilohertz, 1 megahertz, 5 megahertz, even 10 megahertz RF bandwidths. If you were going to be using wide bandwidths like that, you want to make sure that your meter has sufficient bandwidth to make those measurements. So that's another point that I wanted to make. Another thing, in case you didn't have a meter like this or like that, but let's say you did have something like a regular Fluke or whatever DVM, and let's say it was a true RMS reading meter, but it didn't have a dB scale, like this one here does not have any kind of a dB scale. A lot of the newer DVMs are really slick, and they actually have scales that can be displayed in dB. But if it doesn't, but it still is a true RMS reading meter, it'd be a pain in the butt to do so, but you still could manually take voltage measurements and convert them over to dB and look for that 3 dB difference. So you're not totally sunk, you'd just be doing a lot more work. That's why I mentioned early on why it's so convenient to use a meter like this that's got a scale in dB already. It's very convenient to work in decibels rather than voltage levels. So if you've got a meter like this, not this exact one here, but something similar, you can take the voltage measurements, look at the difference between those voltages, convert it over to a dB by using 20 times the log of the difference between those two voltages, one divided by the other, and that'll tell you what you're after. One very, very final note is the cables that we use. Notice the way I've got this laid out. I had the output for the generator coming over here to the step attenuator, going over to this cable. Ideally, I mean, I could have put the receiver someplace over here so that I don't have to run a very long piece of coax. But it's always a good idea when you're working with very, very weak RF signals like this. Remember I said make sure that you use a very high quality double shielded cable like RG142 or RG223. You want to do that because coaxial cables and their shields have a limited amount of shielding effectiveness, and these cables are double shielded. The conductors are silver coated, and they actually provide very good shielding effectiveness. When you're putting a signal coming out of here that's at a minus 140, sometimes 150 dBm, that's an incredibly small signal. And it doesn't take a lot, for example, for a strong signal, like let's say I had a minus 20 or minus 30 dBm signal coming out of the generator, and if I had my coaxial cables all lumped up nearby, and I had this output coaxial cable nearby these other cables, there could be a lot of crosstalk between the cables because of the limited shielding effectiveness of the coaxial cables. So the physical layout of your cables makes a difference. Lay them out in a nice orderly manner where one is not near the other. That'll make a difference. And don't skimp. Don't use cheap shielded coaxial cables. What I could actually do, and I may do this, let me actually turn this off and I'll show you what happens. I'll quickly illustrate how easy it is to get cross coupling between coaxial cables. Okay, so this is just a real quick demonstration, and excuse me for making this video longer than what I said it would take, but I just wanted to show you the pitfalls of what happens if you use cheap coaxial cables when you're trying to make very sensitive measurements working with very low RF levels like we do with MDS measurements. When you're looking at minus 120, minus 130, minus 140 dBm signals. What I've got here, I've set the generator to 0 dBm right at 144.2 like our MDS test. These are brand new RG58 jumpers, and let's say you were kind of sloppy in your setup. You got the generator output just coming around, and let's say it just takes off. I've got it terminated down there at the far end, and then the spectrum analyzer, let's say that was, we're going to be using that as a detector. also an RG58 cable, and it just loops around, goes underneath, comes out, gets terminated into a 30 dB pad, so you can call that terminated. Let's just say you were sloppy and you're using cheap cables like this, and you weren't careful about it, where you placed them or whatever. Take a look at the coupling that we have between these two. So that's really scary. You know, we're looking at a level of minus 71 dBm. We're putting 0 dBm into the cable and we're measuring 71 dB coming out. That's horrible. And what it means is we have a total shielding effectiveness between these two cables of just over 70 dB. That means theoretically each one of these cables only could have a shielding effectiveness of about 35 dB. What that really means is that if I had this signal generator set to a high level of, say, minus 40 or minus 50 dBm, and the shielding effectiveness was only 35 dB, it could be very easily coupled into the cable, blowing right past things like a step attenuator and ending up on the other side. So that's called RF blow-by. That's actually what happens inside signal generators, inside the attenuators, and why their accuracy goes down when you're trying to measure or trying to set very low levels of RF. So be very, very careful with cheap cables. Don't use them to make sensitive RF measurements, or when you're trying to make MDS measurements when you're expecting low levels. There's a lot of leakage occurring in these cables. Not only are they emitting RF, but they're also susceptible to RF. Also means that if your environment is noisy, you got fluorescent lights, you've got these new LED lights, all of them have switch mode power supplies, they're noisy as heck. All these type of noise and inadvertent signals could easily be coupling into cheap coaxial cables. So this is just a real quick demonstration to show you what can happen and how much coupling you can get. Each of these cables, like I said, theoretically could only be producing about 35 dB of shielding effectiveness. So always use a good quality double shielded cable, something like an RG142 or RG223. So okay, let me get this put into the rest of the video. I just wanted to explain to you why the importance of the layout of starting out at one end, putting your step attenuators in the middle, and then putting your rig over on the other side, and not being messy with your cables and letting them be close to one another. Especially don't put them parallel together the way I have here. That's the worst case scenario. And by all means use good quality cables. Okay, so we're back. I've got the signal generator output connected to the step attenuators, and I've got a piece of RG223 with a small bullet going to some RG142 over to the PL259 connector with the TS2000. One thing that you should make sure that you're doing is MDS will change depending on your receiver's bandwidth, and a lot of standards like the ARRL standard make their measurements with a 500 Hertz bandwidth. You can actually make it with any bandwidth that you want. For example, if you're interested in the sensitivity of your receiver for sideband use, you might want to open up the bandwidth to 2.7 or 2.8 kilohertz and measure the MDS that way. Of course, it's pretty easy to calculate what the MDS would be if you've made measurements at one bandwidth using the log of the difference between the two bandwidths. You can calculate what the MDS will be at a different bandwidth. But here I'm just going to start out with 500 Hertz. If your radio has the capability to turn off the AGC, go ahead and do so. Some radios, the MDS will vary depending on what the AGC is set to or whether it's even on or off. I found that on this TS2000 it's pretty interesting, but the AGC really didn't have much of an effect. The Flex 5000, on the other hand, made a huge difference on how the AGC is set to the MDS value. So if you can, turn off the AGC on your receiver. Make sure there's no RF attenuation enabled. You want the RF attenuator off. If it has a preamplifier, turn it on. Make sure that the RF gain is turned up all the way. And the only thing we're going to be messing with at that point is we're going to be playing with the volume control, the AF gain, and we're going to tweak the main dial tuning frequency. So right now I've got a small signal. We've got the Marconi set to minus 90 dBm. Currently have about 30 dB of attenuator coming in. We've got an additional dB of loss from all the cable length here. And then I've got the audio output of the receiver. In this case I'm using an 1/8 inch auxiliary speaker output connected directly up to the HP True RMS meter. You could use just as easily the headphone jack if you wanted to, or you could use the 1/8 inch plug on the back the way I did. So when we go ahead and turn up the volume, you can see in fact that there's our carrier. I've tuned slightly off frequency and we're getting a reading on the meter. The very first step that you want to do is, with a fairly strong signal, you're going to come up to the main dial and we're going to tune it back and forth. And what we're going to do while we're tuning it forwards and backwards, we're going to be looking at the meter and we're going to look for the peak. Notice we're not going to be adjusting the radio for the exact frequency of the carrier. What we're going to do is we're going to find where it actually peaks. So I think someplace right about there is the peak. It ends up being right at 14200.13. And it's really irrelevant. But the point being is that in the IF filters of the radio, that carrier now is at a peak. If the IF filters were absolutely flat, it wouldn't matter. We could line up the carrier anywhere within the passband. We would set it for, say, the middle of the passband, and it'd be okay. But every real filter, with the exception of software-defined filters, well, even they have some small ripple, but real mechanical filters and things like that will have a small amount of ripple, and you'll find that as you tune across the passband, the amplitude will go up and down, just as we saw there. So we went ahead and found the frequency. We tuned the radio to where we got the maximum response from that carrier. And what we're going to do is we're going to adjust the volume level. Notice the scale here is irrelevant. I've just picked an arbitrary scale to where I'm getting a convenient reading on the meter. And in this case, I've just adjusted the volume so that it's in the ballpark of about 0 dBm. Now the idea is to perform the MDS measurement, we're going to turn off the RF source from the generator, and we want to see that meter drop exactly 3 dB. In other words, we want to see a 3 dB difference with a carrier versus without a carrier. Now at this very strong level that I've got, since I've only got about 30 dB of attenuator put in, let's see if I can hold this steady enough. I'm going to go ahead and turn off Notice that by turning off the generator, we dropped way more than 3 dB. You can see that there's a 5 dB, 10 dB. I mean, we're clear down into nothing. So that means that we were putting in too strong of an RF signal. So we go ahead and turn it back on, and what we're going to do is we're going to advance this control. Let's put in 40 dB of attenuation. Notice now that the voltmeter has dropped its amplitude, and what I'm doing, it's perfectly acceptable. We're never ever going to touch that dial again, the frequency dial. Leave it alone. But it is okay at this point to take the volume control, and we're going to bring up the volume. And again, we could leave it anywhere we want, because we're going to be just looking for a 3 dB difference. But I like bringing it up to about the 0 dB level. Now, notice as these signals get weaker and weaker, the meter is going to start bouncing around a little bit. You're going to get variations. That's one thing nice about an analog meter. Digital meters will bounce around. The numbers can be kind of hard to read. An analog meter like this actually has advantages, is that it has some inertia and it's easier to get average readings. So there's about 0 dB. What I'm going to do is turn off the signal generator, and you can see once again we've dropped down now to about 9 dB. So we're getting closer. We want it to drop 3 dB, but we're dropping about 8 or 9 dB. So that means our signal is, again, it's too strong. So what I'm going to do now is I'm going to start dialing in 1 dB increments. And let's put in about 9 dB here. And let's leave that set to 40 and 9. So we've got 49 dB. Again, the meter level has dropped because we're putting in a much lower level RF signal. What I'm doing is bringing up just the volume control. We're not touching the main dial at all. As I bring up the volume level, and this is going to be the tricky part. You're going to see it's starting to bounce around on us. It's going to go above and below, so you're going to have to make a judgment call where you think about 0 is. So let's say that it was about there. I'm going to come over here. I'm going to just disable the RF carrier, and lo and behold, there it is. There's about a 3 dB delta on the meter. Now that we found, I'm going to go ahead and turn this level down. We don't need to be listening to that background noise. I'm going to pan over here. Now that we found the level, the RF signal level, that resulted in a 3 dB delta with the carrier on and off, all we have to do is calculate what the absolute RF signal level going to the receiver was. Well, we're starting out with a minus 90 dBm signal. We're coming through here, we've got 9 dB, and we've got 40 more dB here, so we're looking at minus 139 dBm at this point. And we know we've got about a dB loss going through all this coax, so it's pretty safe to say that with as an absolute measurement, this is not a relative measurement, this is an absolute measurement, we can say that the MDS level at 500 Hertz for that receiver is minus 140 dBm. So let's remember that number, minus 140 dBm. Okay, so now what I've done is I've taken the audio output from the receiver, and rather than going to the analog meter, I've got it going to the Fluke digital meter. And this is where it's going to be kind of difficult. You can see the random noise is bouncing around quite a bit. I'm going to go ahead and see if I can zero that. So there it is, pretty close to 0. I'm going to bring up the volume just a little bit. There we go. So it's toggling someplace between some negative value and just above 0. I'm going to go ahead and now turn on the SIGGEN, and you can see that we're bouncing around that 3 dB difference. And actually, we are a little bit high. I could bring the volume down just a little bit. There we go. We're toggling between negative numbers and positive numbers. And you can see right there, there's about a 3 dB difference. So that's, and we're using the same numbers that we got before. So again, we've got minus 90, we got 9 dB plus 40, so we're looking at minus 139, and we can safely add a dB of loss in this cable at 2 meters. So we're looking at an MDS level of minus 140 dBm. That's at a bandwidth of 500 Hertz on 2 meters with its preamplifier on, and the AGC in this case is set to its absolute fastest position. So let me show you a very neat and simple way now. What we can do is take this number, the MDS value, and we can go ahead and calculate an actual noise figure number, which can be very handy. So let's do that next. Okay, so this is the very last part of the video, and I'm going to show you how you can use the MDS value to calculate the noise figure of your front end. So to keep this real short and sweet and simple, let's just remember, thank you Mr. Boltzmann, because of his constant that he was able to derive. What we know is that a 50 ohm resistor at room temperature can generate a noise level of -174 dBm per hertz. That's a constant. So that's fact number one. Number two, we measured an MDS at 500 Hertz, not 1 Hertz. Notice that formula above, -174 dBm per Hertz, that's the amount of noise for 1 Hertz of bandwidth. We didn't do our measurement in 1 Hertz, we used 500 Hertz. Because of that, we need to calculate a correction factor. So that's step number 3. Correction factor is pretty simple to calculate. All we do is take 10 times log base 10 of the bandwidth that we made the MDS measurement in this case 500 Hertz, divided by 1 Hertz. That simplifies to 10 times the log base 10, 500, comes out to 26.99. We're going to round that off to 27 dB. So a correction factor of approximately 27 dB will be used in these calculations. Next point, number 5. A perfect receiver's noise figure would be -174 dBm per Hertz plus the 27 dB, because it's 500 Hertz bandwidth. That comes out to -147 dBm. I tried to squeeze in up above there. 147 didn't look too good, so I just rewrote it. It's -147 dBm. Alright, that's step number 5. Number 6. For RTS 2000 with an MDS of -140 dBm, what we can say is this: the noise figure is going to be it's going to be 147 dBm minus the dBm value that we got for the MDS, which in this case is 140 dBm, and that's at 2 meters, of course, which comes out to 147 dBm minus 140 dBm, or 7 dB. So what we can say is that the Kenwood TS2000 on 2 meters, its front end has a noise figure of about 7 dB, which is actually not too bad at all. It's actually a pretty hot receiver. Notice that if you were to add an LNA in front of this, let's say you had a LNA that had a noise figure of 3/4 of a dB, it would help substantially this receiver detect very weak signals for moon bounce, EME, or meteor scatter, things like that. So this is a easy way to calculate what the noise figure of your front end is. It's also an easy way we showed you to measure the MDS of your receiver. And using this information, you can then determine if you need a preamplifier, and if so, what kind. So I hope you found this video helpful. I'll go ahead and post it, and if there's any questions that come up, please let me know. Feel free to email me at my call at mchsi.com. 73.